All right, so let's check out homework 7.1. And just as a quick refresher, this homework is going to be all about work, where work is going to be whatever force we're interested in times whatever the displacement of the object is, the distance it travels. And there's also a cosine theta here, where theta is the angle between force and the distance traveled. So let's say I have my object here on some surface, and if I push it with this force, it'll then travel this distance direction. To get the angle, we want to put these two vectors tail to tail. And if we do that, there's zero angle here. And so cosine 0 would give us a 1. But let's say instead I was pushing kind of up on this box. Well, it's still going to move this way. And then when we connect these two vectors together, tail to tail, this is the angle that's going into the work formula. So we have to connect these vectors tail to tail, and that angle that we get there is the angle in cosine theta. So most of the time, the angle will be given to you in the problem. And maybe you might have to figure it out, but usually the angle is given for you. So let's check out this first one. And there's a lot of wording here about a tractor pulling some lumber. And let's just go right to the question now. And it says, suppose this tractor pulls this lumber horizontally. So instead of the angle. So when they tell us it's pulling it horizontally, that means the force is going to be in the same direction. So here's my sled, and it's being pulled with a force. They're saying that's horizontal. And the sled's also going to move this way. So connecting those two vectors tail to tail will give an angle of 0 for our work formula. And so cosine 0 is 1, which means this just reduces to the force we're interested in times the displacement that's happening. Now, this question, the actual question is, what is the total work done? Now, there's two ways to get total work done. One way is to look at all the forces individually and see what they contribute for work. Another way to get the force, the net work, is to use the net force. So if you want the total work done, this actually equals what the net force is times our displacement. And let me give you an example of that with the sled here for this problem. Is that here's a free body diagram. So the sled has some weight, the normal force from the surface holding the sled up, and then there's an applied force from the tractor pulling on it. And this problem does say that there's friction in this problem as well, the force of friction. So one way to get the total work is to look at the work done by each of these individual forces. Now our displacement is to the right. That's our displacement. So let's just take the normal force. How much work is done by the normal force to hold up this box? How much work is done? Well, if we connect these vectors tail to tail, there's the normal force. Here's our displacement. This is actually a 90-degree angle. So the angle between these vectors connected tail to tail is 90 degrees. This is the theta that we're interested in for our work. But cosine 90 is 0. So the work done from the normal force is 0 because it's perpendicular to the motion. And this should make sense. I mentioned this in class where I had the paper towel thing in a desk, and If I want to push the paper towel to the left, I'm not going to accomplish that by pushing straight up. And that's the same deal with this picture. How can the normal force be doing any work when our motion is to the right? You can't push up to make something move right. And so the work done by the normal force should be 0 here. It's not contributing at all to the motion to the right. And what ultimately gives us that answer is the cosine. So whenever you have 90 degrees like this, cosine 90 is always 0, and the work from that will be 0. Same with the weight. If we look at the weight, because that's straight down, and connect it with our displacement, we again get a 90-degree angle, and cosine 90 is 0. And so the work done by gravity is also 0. So in other words, pulling down on the box doesn't make it move to the right. So gravity is doing nothing. Gravity is doing nothing at all to push the box to the right. So the work done by gravity is 0. Now, the two forces that will do work are the ones that are vertical here, like the force of friction. We look, the force of friction is to the left, but our displacement is to the right. Now, a straight line in geometry is technically 180 degrees. So when I connect these vectors tail to tail, this time with the force of friction, they actually form a straight line. The angle between them is 180. And if we take 180 and put it back into our work formula, cosine 180 is -1. And so if we look at the work done by friction, we will have cosine 180, which is minus. So we would have minus the force of friction times the displacement we're moving through. So friction is doing work here. Remember, a minus sign means it's taking away energy, taking it away. And if we look at the force applied going to the right, and our displacement also going to the right, and the angle between these is then 0. And that's the angle we would plug into our formula. Cosine 0 is 1. And so that just leaves us then with the work done by the applied force would be the applied force times the distance traveled. So one way to get the total work done is to look at all the forces, in this case we had 4 of them, and just add all of these together. And so we would get our total work would be from the force of friction and from the force applied. Since the normal force and the gravitational force are not contributing to the motion to the right. And if we look at our problem here, to the right over here, they actually tell us what the force of friction is, 4,900 newtons. So they're telling us that the force of friction is 4,900 newtons. And they're telling us the displacement, the distance traveled, is actually all the way at the top up here, where they say the sled travels a distance of 20 meters. So our D is 20. That's how far we're going to pull this sled. And we're adding to that the applied force. Now the applied force is also in this top part. It says the force from the tractor is 5,000 newtons. So the applied force from the tractor, 5,000 newtons. And again, this sled's being pulled a distance of 20 meters. And this is our total work. And if we just add all that together, we would get 20 and then times 100. So 5,000 minus 4,900 is 100. And that's ultimately multiplied by 20 to get us 2,000 joules. So the net work, the total energy, is 2,000 joules. Now we can also get this by looking at the net force. So let me just show that. So 2,000 joules, our answer there, and that means we should get the answer again. So let me just draw the free body diagram really quickly. Force applied, force of friction. So we know our motion is to the right. That's our displacement. The forces in the y direction, normal minus mg, there's no motion in the y direction, so that just equals 0. Our motion is all in the x direction. We have the force applied to the right, force of friction to the left, and this is accelerating. So this equals ma, where ma is the net force. So we can use the net force to also get the total work done. So if we look at the net force, it's going to be the force applied, 5,000, minus the force of friction, which they're telling us is 4,900. So the net force is 100 newtons. That's the net force. When we have the net force, we can then go right to what the total work done is. Because the total work will also equal the net force times your displacement. Our net force is 100. We're doing a displacement of 20, and so we get our 2,000 joules again. And so this is a way you could check your work, and that's why this problem's got a lot of like this big blue box here on the right. That's why there's a lot of wording there. So this first part, what I'm highlighting, sorry about that, my phone interrupted me there. What I was saying is this is what they're doing here in Mastering Physics, what I've highlighted. They're doing all the individual forces, so you can see they have work tractor, work weight, work normal, work friction. This is one way to get the total work, is to add the work together from every force. And then at the bottom here, they actually show you that you can get the total work also from the net force. And they don't quite clearly state that this is the net force times displacement here. It's not quite clearly stated, but that is the second answer here. And you can see they get the same answer either way. And again, a way to check your work. So our answer there is 2,000. So let's check out the next one. We got a ball is thrown straight up. How does the sign of the work done by gravity while the ball is traveling upward compare with the sign of the work done by gravity while the ball is traveling downward? So here's our ground. Here's our ball. And it's going up. So that's our displacement. Displacement is going up. But the force of gravity is going down. So the work done by gravity, I'll call this going up, is going to be, so connecting these tail to tail means there's 180 degrees between these vectors, connecting them tail to tail. And our formula is FD cosine theta. So the angle between them is 180. Cosine 180 is minus. We get a minus force of gravity times displacement. And, you know, our force of gravity is mg. And so that's the work done by gravity as it's going up. Gravity is taking away energy. And that's why the ball eventually slows down, because it's losing its energy as gravity takes it away. Remember, the minus sign means you're taking away that energy. And that's why the ball eventually slows down and falls back to the ground. It loses its energy. And then they're asking, okay, well, now the ball is falling down. All the ball's falling down. Here's our displacement. Our displacement is down. The force of gravity is also down. So when you connect these tail to tail, the angle between them is 0. And a 0 we plug into our cosine. Cosine 0 is 1. So the work of gravity going down is going to be positive. Now it's positive force times displacement, where the force here is gravity, and so we get mgd. And hopefully that makes sense, because as the ball falls to the ground, it's getting faster and faster. And that's because gravity is now adding energy to the ball. So before, when you threw the ball up, you got a minus sign because gravity is taking that energy away to slow it down. But when the ball is falling to the ground, it's now speeding up, which means it's gaining energy, and it's gaining that energy from the gravitational field. So let's see what the actual question here is. While the ball is traveling upward, compared with the sign of the work as it's going downward. So let's see. The first selection here is work done by gravity is negative while the ball is traveling both up and down. Well, that's not true. It's only negative going up. It's positive going down. Let's see what the next one says. Work done by gravity is positive while the ball is traveling up. No, traveling up, work is negative because the ball's slowing down. So gravity takes that energy away. Let's look at the next one. Work done by gravity is negative while the ball is traveling up. So there we go. Ball traveling up. We get negative work. That's good. And positive while the ball is traveling down. And we do get positive work when the ball is traveling down. So selection C is our answer. Let me just look at the last one now. Work done by gravity is positive while the ball is traveling both up and down. So that's not true. It's only positive when it's traveling down. And again, just to say this again, to help it make sense, when you throw something up, it slows down and then falls back to the ground. And that's because the gravitational field is taking energy away from this object until it has no energy left. And so it has to stop. And then gravity will put energy back into it as it falls down. And then the object gets faster and faster until it hits the ground. So there's our answer, C, or the third selection there. Now we got our fisherman reels in a 15 meters of line while landing a fish, applying a constant force. So, well, there's my fish. And now there's no angle given, so we're going to assume this is horizontal. Does it actually say that? It doesn't. But because there's no angle, we have to assume this is horizontal because there's no angle given, and there would be no way for us to figure out an angle here because there's just not enough information for us to do that. And in general, that's going to be true. If there's no angle given in a problem, chances are then things are horizontal. So there's a force. The force is pulling on the fish. And the fish's motion is also in the same direction. So we have a force applied from the fisherman pulling the fish in, which means the fish is going in the same direction as the force is. So when we connect these tail to tail, the angle between them is 0. So when we look at our work done, FD cosine angle between them, well, the angle between them is 0. And so cosine 0 is 1. And this reduces to just force times displacement. And they tell us the force. So just looking at the problem, they tell us the force 35 newtons. And they're telling us the displacement is 15. And that is 525 joules of work. So that fisherman had to expend 525 joules of energy to reel in that fish. Let's check out. Oh, this is meant to be a J for joules. We'll check out the next one. So now we got a boat. Now this time it does say horizontal, so that's good. So there's no confusion here. This is horizontal. There's no angle here. A boat with a horizontal tow rope pulls a water skier. And the rope makes an angle of 14 degrees. So we're going to need a top-down view for this one. So if I try to draw my boat sideways and my skier over here, well, it's hard for me to indicate this angle given of 14 degrees. So we'll need a top-down view picture for this. So looking down on the boat, there it is. And the skier is off to the side at 14 degrees. So our skier is off to the side by 14 degrees. And we're given some info then. It says if the tension in the rope, so the rope pulling the skier, if that tension is 200 newtons, how much work does the rope do on the skier during a displacement? So now they're giving us a displacement here of 350 meters. So let's take a look. Tension on the skier. Let me just draw the skier for a moment. Remember, we're looking down at a skier, so there's the top of their head. And there's a tension that's pulling them this way. And our angle here, 14. And their displacement is this. That's their displacement. So the angle they gave us, 14, is also this angle right here, 14. So this is just a rectangle with its corners like that. So these angles are the same. These two angles are the same because it forms a rectangle there. So just using a little geometry to get our angle over here. Our vectors are connected tail to tail. We find our angle between them to be 14 degrees. And we'll look at how work is defined, FD cosine theta. The work done is by tension. They're asking if the tension in a rope. So our force here is tension. And they're telling, well, let me just write it in as tension. We have our displacement. And then cosine of the angle between them is 14 degrees. So they are telling us the tension, 200. They're telling us the displacement, 350. That's all times cosine 14, which equals that, which is a lot of joules. 67,000. Actually, it's 679,207. So I will write that in. Oh, I'm sorry. There's a decimal point here that I didn't write very well. But it is 67,920.7. And that's too many sig figs, so the programmer will probably round it, and it did. It rounded it to 6.8. So they are using scientific notation. Let me just take this number and just write it up here where I got some room. So our number here being 67920.7. For scientific notation, usually you like to have the decimal place right here. In other words, a single digit, then a decimal place, and then the rest of your number. So 6 points at 7.9. So the 7 will be rounded to an 8. And to get the decimal place over here, we'd have to move it 1, 2, 3, 4 times to get the decimal place there. And so that's how they get the 10 to the 6.8 times 10 to the 4th joules. Check out the next one. So let's see, we have a rope, just reading the blue part here, tied to a box. All right, I can draw that. A rope tied to a box. Let me just see if there's any angle here before I draw my rope. The rope makes an angle of 30 degrees with the horizontal. All right, so there's the horizontal. The rope is making 30 degrees with the horizontal. It pulls the box 1.3 meters. And it also says with the tension, it's giving us a tension in a rope is actually 5 newtons. So the tension we're given that's in the rope that we're pulling on as being 5 newtons. And there's also an opposing friction force between the block and the floor. And so we have a friction force here, opposing motion, and they're actually telling us that one is 1 newton. So there's my picture. It might be helpful to still go back to free body diagrams here, since we have our tension going off this way at 30 degrees. We have the force of friction, opposing motion. We have the weight going down and the normal force going up. That would be our free body diagram here. Now our box is going to move to the right because, we're pulling it to the right. So it's going to move to the right. That means the normal force and weight are both perpendicular. So there's the normal force. Here's weight, and they're both perpendicular with displacement. That means 90 degrees, and cosine 90 equals 0. And so when we look at our work formula of FD cosine theta, if cosine theta is 0, then the work done is 0. So the work done by the normal force is 0, as well as gravity. So what is doing work is the tension and the force of friction, because these are in the horizontal plane that the box is actually moving in. So the box isn't moving up or down, so up or down forces are not going to affect how you're moving left and right. So they want how much work. Oh, well, the first question is, if I look over here, how much work is done by gravity? Well, as I just argued here, the gravitational force, 90 degrees with our displacement, and cosine 90 is 0. So the work done by gravity is 0. If we look at the next one, how much work does the tension do? So now we're going to need a little bit of work here. Tension. There it is. There's tension. And here is our displacement, how the box is moving. We have to connect these vectors tail to tail, and the angle between them is the theta in our work formula. And you can see by looking at this picture here that theta is 30 degrees. So if we look at the work done by tension, again, it's FD cosine theta. The force here is tension, and we're moving this a distance. And then we have cosine 30 because the angle between them is 30 degrees. And they gave us numbers. They told us the tension is 5. They told us the displacement is 1.3. And then cosine 30. And that equals 5.63 joules from tension. And part C, how much work does friction do? So friction, let me try to write off, I guess, the side here. Friction, going this way, that's the vector. Our displacement is going to the right. The angle between these two vectors is 180 degrees. A straight line is 180 degrees, and cosine 180 is -1. So when we look at our work formula, FD cosine theta, you know cosine theta is -1. So this is going to be minus force times displacement. The force of friction, they told us, is 1. They told us the force of friction is 1. And the distance traveled is 1.3. And this is the work done by friction. Work done by friction is going to be minus 1 times 1.3 to get us a minus 1.3. Part D. How much work does the normal force do? Well, I talked about that earlier. How the normal and weight, these are both perpendicular to the motion. Perpendicular specifically means an angle of 90 degrees, and cosine 90 is 0. So the normal force does no work. Again, pushing up isn't going to make the object move to the right. So how can a normal force do work? How can you push up and have something move to the right? So the normal force contributing nothing at all to the motion. And then part E wants to know the total work. And again, there's two ways we can get this. We can either get the total work. We can either get the total work from the net force times displacement. Or we can get it by summing up the works that from all the forces we have. So we have the work of tension, the work of the normal force, the work of gravity, and the work of friction. So both these will equal. These are the two ways you can get the total work. Now in this case, I'm going to go with the second one here. And the reason I'm going to go with the second one is because this problem already told us to work through these individual works. We already did that. So if I look at what we have, our work tension was 5.6. So the work from tension was 5.6, plus the work from the normal force, which was 0, plus the work from gravity, which was 0, and then our work from friction was minus 1.3. So we had, I'm just running out of paper here. So let me just write this again. Work from tension, the work from the normal force, the work from gravity, and the work from friction is negative because friction always takes away energy. And then this is the total work. You can always get the total work by adding all the works done from each force. And so we get 4.3. 4.3 joules of work is the total work, the total amount of energy that went into the system. Now, if you wanted to check this with the net force, we would have to get the net force coming off of our free body diagram again. So the net force is just in the x direction because we're just pulling it right. So if we would look at the sum of the forces in the x direction, we have this component of tension. We have this component, the adjacent angle. We get the adjacent angle from cosine. So this adjacent here is t cosine 30. That's to the right. To the left is friction. And Newton says this has to equal ma. Ma here being the net force. Because the sum of the forces in the y direction is 0. So the net force is all coming from the x direction. And they told us that tension is 5. And they told us the force of friction is 1. This is the net force. So if I want to get the total work, that's the net force times displacement. Our net force is 5 cosine 30 minus 1 times our displacement, which was 1.3. And I will just punch at my calculator to check it. Gets 4.3 joules, which is the same answer we got before, and it should be. So just to state that again, there are two ways to get the total work done. You can either do the total work from the net force, or you can get the total work by summing up all the individual forces. So we had tension, normal, gravity, and friction. So these are the two ways that you can always get the total work done. Check out the next one. We got a factory worker moving a crate that distance, and they're pushing it horizontally. So I usually look for an angle right away so I know how to draw my picture. They're pushing it horizontally, so I know how to draw my picture now. We got our worker. They're pushing on the box horizontally. That's force applied. And the mass here is 26. The distance they're going to move it is 5 meters. An important statement here is constant velocity. Constant velocity is actually a very important statement here. Constant velocity means there's no acceleration. That's what constant velocity means. It means you're traveling the same speed. You're not going faster or slower. The same speed means zero acceleration. And since the net force is also equal to ma, if there's zero acceleration, then the net force will be 0. Which means the net work, the total work done, which is net force times displacement, will be 0 because the net force is 0. And that's why this constant velocity is an important statement here. That's telling us that the acceleration is 0, which means the net force is also 0. And if you're curious, well, how could that be? How could something be moving but have a total work of 0? And that's going to be because, and we'll see with the math in a second, that's because the force applied by the worker, all of that force, all the energy they're putting into that is being consumed by friction. And so it's not speeding up because the friction's taking that away. And it's not slowing down because friction's not overcoming this force applied. They're balancing each other perfectly to get a constant velocity. So if we looked at our free body diagram here, we got normal up, weight down, our force applied, and then there's a force of friction. And if we sum these forces in the x direction, force applied to the right minus force of friction to the left, Newton says this equals ma, but they're telling us there is no acceleration, so this equals 0, which means the force applied must equal the force of friction for that to be true. But let's take a look at what the actual questions are. So it says, what magnitude of force must the worker apply? Well, they must apply that which is equal to the force of friction. And if we look here, they give us some more information. They tell us the coefficient of kinetic friction, what they're telling us there. So they're giving us mu 0.2. So from this statement here, the statement ultimately from constant velocity is that the force applied must equal the force of friction. The force of friction is mu n. It's always mu n. This is mu s for static, and then mu k for kinetic. Kinetic means once you're already in motion. The normal force, we look back to our free body diagram, in the y direction is just normal up, mg down, and that equals 0 since it's not moving up or down, which means the normal equals mg. And so we have mu k, and the normal force equals mg. And if we look, they are telling us these numbers. That's 0.2. The mass, 26. And g is 9.8. And we get 50.96. So 51 must be that net force. Or not the net force, I'm sorry, the force of being applied from the worker. And they'll probably round that to 51. Yeah, 51 newtons. So how about part B? How much work is done in a crate by the worker's push? So now they're asking for work. How much work is being done by just the worker pushing it? So if we look back, here's the worker pushing it. They're pushing it in the same direction as our displacement. So when we connect these vectors tail to tail, the angle between them will be 0, and cosine 0 is 1. So if we want to look at that work done by the person, it's just going to be their force applied. Oops, I guess you can't see that. Work done by the person is just going to be the force applied times the distance traveled. And we just figured out what the worker's force is from the previous problem. We'll use their number of 51 there because that's the rounded number there. And then the distance traveled is 5. And so we'll get 255 joules. Part C. How much work is done by friction? All right, well, if we go back and look at our pictures here. Here's friction going to the left, but remember, our displacement is going to the right. So when we connect these vectors tail to tail, so displacement to the right, friction to the left, this is 180 degrees when we connect these tail to tail, and cosine 180 is -1. So when I look then at the work done by friction, cosine 180 is minus, and then we have the force of friction times our displacement. So friction should always have a minus sign because it takes energy away. And that's what the minus sign means. It means it's taking energy away. The force of friction, we know from right here, force of friction is mu kmg. That is the force of friction. And then times our distance traveled. And these are all numbers we know. This is minus 0.2, the mass 26, g 9.8, and our distance traveled is 5. So minus 254.8. And I'll probably round that to 255. Part D. How much work is done by the normal force? Well, the normal force is perpendicular to the motion because the motion's to the right. Perpendicular specifically means a 90-degree angle, and cosine 90 is 0. And that's the math way of saying it. The physics way is, how can I push up on something and have it move right? So the normal force is pushing up. That puts no energy into moving something to the right. If you push up, then something's going to move up. If you push up, you're not going to get something moving to the right. So pushing up adds no energy to the motion to the right. So we'll get 0 there. And then finally, part E. What is the net work done? So this goes back to what I was originally stating here about constant velocity. They told us is that constant velocity, the net force is always equal to ma, but they're telling us constant velocity, which means a is 0, because that's what constant velocity means. There's no acceleration. And if there's no acceleration, the net force is 0. And so when we look at the work equation, and if we plug in net force, well, if net force is 0, then so is everything else. Because all these other numbers times 0 is going to get you 0. So the actual net work is 0. So that specifically means the amount of work you're putting into the system is exactly being taken out. So all the effort this worker is pushing with this box, all their energy is being consumed by friction. And so they're only able to move the box at a constant velocity. They can't make it move any faster. They'd have to push harder to overcome how much energy friction is taking away. Let's check out the next one. A tow truck pulls a car. So this is in kilometers. We're going to need to fix that and put it in meters. So we got, and it's horizontal, so there's no angle here. And a cable. Okay. So here's our car. And it's being towed. And it's going to travel a distance of 4.3 kilometers, which is 4,300 meters. And what else do they tell us here? The tension in the rope is 770. And they want to know, part A, how much work does the cable do on the car? Okay? Well, the cable, the tension is to the right. Displacement is also to the right. So connecting these vectors tail to tail gives us an angle of 0. Cosine 0 is 1. And so we get just force times displacement. The force we're looking at here is tension. And they told us, they're telling us the tension is 770, and they're telling us the displacement is 4,300. Which is, now this is a larger number, so I'm going to write this in scientific notation, because that's what my calculator is giving it to me now when the numbers get larger. 3.3 times 10 to the 6 joules. And I'm actually not quite certain how to enter scientific notation. Let me give it a whirl. So 3.3, 10. So I need to get an exponent. Looks like there's the exponent. 10 to the 6. So there we go. That wasn't too bad to enter in there. Part B, how much work does the cable do on the car if it pulls at an angle? Okay, so let me just draw another quick picture for that, just so you can visualize it. So now it's being pulled at an angle. And they're telling us 34 degrees. This is the displacement. The displacement is to the right. The tension is now at 34 degrees. These vectors are connected tail to tail. So this is the theta in our work formula. The force is tension, which you're telling us is 770, times displacement, which is 4,300, and then cosine of the angle between them, which is 34. And that equals 6. So the number is getting kind of large, so my calculator is giving that in scientific notation. Nothing wrong with that. Just maybe a little bit harder to type in. Part C. How much work does a cable do in a tow truck if it pulls horizontally? Oh, interesting. All right. Let me draw another picture then for that. So now they're asking us to focus on the truck. So that may be a little bit of a confusion here. So A and B were having us focus on the car. But now part C is asking us to focus on the truck. So the truck has a tension that's pulling it backwards. That's the tension connected to the car. The truck is, I'm assuming, going to travel the same distance as the car since it's towing it, 4,300 meters. And the tension, they told us, is 770 newtons. Our displacement is to the right. Connecting these vectors tail to tail. Tension. Displacement. That's 180 degrees. So when we look at work, Since the angle is 180 degrees, cosine 80 is negative. The force we're interested in is tension, which they told us is 770. And the distance that has to be traveled is 4,300. And this is the same answer that we got for the part A, 3.3 times 10 to the negative 6, except this one is minus. So 3.3, but minus. And just to be clear, the minus sign comes from because we're looking at the truck now. And from the truck's perspective, tension's going to the left. Their displacement is to the right. And that angle between those two, connecting the vectors tail to tail, that angle is 180 degrees. And cosine 80 is what pops out that minus sign and makes that work negative. So the tension on the truck is taking away energy. It's trying to slow the truck down. And I think you can imagine that. You know, a truck is pulling a car. If the truck lets off the accelerator, well, the car is going to pull on a truck trying to slow it down. So the truck has to, you know, keep accelerating to overcome this energy loss from pulling the car. Part D, how much work does a cable do on the truck if it pulls at an angle above the horizontal? So now we got our truck, and it pulls at 34 degrees above the horizontal. So here's the horizontal. Here is 34 degrees, which means then the tension is something like that. Our displacement is still to the right. So connecting these vectors tail to tail, which is what I just did here. I connected the tension down here, displacement here. They're connected tail to tail. This is 90 degrees plus this 134 means the angle between them is 124 degrees. So the angle between displacement and tension, this angle here, 124. So when we look at our work formula, we got the force here is tension, which we know is 770, the displacement 4,300, and then we have cosine 124. Which is so again, the tension is pulling back on the truck, trying to slow it down, so it's taking energy away. What? Oh, I'm sorry, that's an 8 right there. All right, I see what I did here. Let me just draw this a little bit better. This is the mess up right here. So let me just draw this picture again. Here is distance, our displacement. Here's our angle. Now the angle they actually gave us here is 34. Here is 90. The angle I actually need to add is this one. So I made a mistake by doing 90 plus 34 to get me that 124. I actually need to do 90 plus this angle here. So using sum of interior angles, because this is 90 degrees, we have 90 and this 34, which is 124, but that has to be 180. So the sum of interior angles has to be 180. So 180 minus 124 will tell us this angle then is 56 degrees. So let me draw that one more time. Here's our displacement. Here's our tension. The actual angle here is going to be 90 plus 56 to be 146. And that's what I'll have to change right here. Change that to 146. So it was the angle that I did mess up on there because the 34 is down here, where we need the angle right here to figure out the angle between these two vectors. So it's 90 plus this angle here, which we just figured out to be 56. If I do that, I'll get this part changes. Minus 2.74. And that's what it is there. So just say again, I did 90 plus 34, which is incorrect. To get the angle between these two vectors connected tail to tail, I actually needed this angle up here in the corner plus 90. And again, that angle in the corner is 56 degrees then. And part E, do I have enough room to squeeze this in somewhere? How much work does gravity do on the car? Oh, well, that one's easy because gravity is straight down and the car is moving to the right. That angle between them is 90 degrees and cosine 90 is 0. So when we look at work, FD cosine theta, theta is 90, cosine 90 is 0, which means that whole thing there is going to be 0. So just say it again. If you put your book on a table and you just let your book sit there, gravity pulling down is not going to make your book move to the right. All right. Check out the next one. We got 2 tugboats pull a disabled supertanker. Each tug exerts a constant force, one at that angle and another at that angle, as they pull the tanker at distance towards the north. So this will need a top-down picture to incorporate those angles there. So I guess here's our big boat that needs to be towed. And at an angle 13 degrees, so one of them is at an angle of 13 degrees west of north. So here's one tugboat pulling on the freight, the supertanker, and the other one is 13 degrees east of north. Oh, so it's symmetric here. So that one's 13 degrees east of north. So there's our other tugboat pulling it. So we have a nice symmetry there, both pulling at 13 degrees. And it wants to know in part A, what is the total work done by the 2 tugboats? What is the total work done? So since the tugboats are doing wait a minute, let me check their, each tug exerts a constant force, okay? So that's the tension here in the rope. 2 times 10 to the 6 newtons. And they both have that same tension. So the boats are basically identical. They're pulling with the same tension at the same angle. And remember our displacement, actually displacement is up because the boats are pulling it. So forget that arrow there. So the tugboats are pulling, so our displacement is up. And these tensions are kind of off to the side. So here is our displacement, it's up. And I'll just look at this right tension. There it is. And the angle between them is 13 degrees. This is the angle for our work. When we look at work, FD cosine theta, theta is 13 degrees. The angle between these vectors connected tail to tail. So our force here is tension. We're pulling at some distance. Cosine 13. And they're telling us the tension. It's 2 times 10 to the 6. That's the tension. They're also telling us the distance in here somewhere. They tow it 0.66 kilometers. So we do need to put that into meters. So that means multiplying that by 1,000. So that 0.660 will be 660 meters. And then cosine 13. This is for one tugboat. Since both tugboats are exactly the same, we're just going to multiply this by 2 when we're done. Or if you aren't satisfied with that, you can do the other tugboat. Here's our displacement. Here's the tension. Again, the angle between them is 13 degrees. And we will get exactly the same formula. We'll have tension, displacement, cosine 13, and that is tension, displacement, cosine 13. We got 2 of these. We can just solve this once, multiply by 2. So just to be clear, it is 1.29 times 10 to the 9th, and that's what I'm going to multiply by 2. To get 2.57 times 10 to the 9th. Now, remember I am rounding right, oops, sorry, I can't quite see that. I am rounding here. So that 1.29 is rounded. And here's 2.57. That's also rounded. And that's our answer. What's the total work done by the 2 tugboats? Well, one tugboat does 1.29 times 10 to 6 joules. And then 2 of them will do that. All right, got another interruption there, but there's our answer, 2.57. That was to the 9th on that one. And there is 8 of 8. And that is practice homework 7.1 and 7.2.